Hello everyone. Now today we are going to discuss about for Cayley-Hamilton theorem. Before going to discuss the Cayley-Hamilton theorem, we must know about for some of the definitions. Now first characteristic equation. Now let A be any n cross n matrix, nothing but square matrix here, n cross n, number of rows and equal to number of columns, therefore is square matrix. Then mod of a minus lambda equals 0, nothing but determinant of a minus lambda equals 0 is known as characteristics equation. Okay, now this expression is characteristics equation. Now next definition, eigenvalue. Then a minus lambda equals 0 is a characteristics equation. Then roots of that equation, okay, the solutions of the equation is known as eigenvalue. Okay, now when look at the example, the better you understood clearly. Now example, let A equal to 1503 is a 2 cross 2 square matrix. Then find A minus lambda I. Now A minus lambda into I. Now the square matrix of order 2 cross 2, I consider the identity matrix of order 2 cross 2. If they given 3 cross 3, then you should take a identity matrix of order 3 cross 3. Here 2 by 2, that's why I take for 2 by 2 identity matrix. Now simplify this. 1 minus lambda into 1. 1 minus lambda. Next to this position, 5 minus lambda into 0. Now this term 0. Now 5 minus 0 is 5. Now 0 minus lambda into 0 is 0. Now 3 minus lambda into 1, 3 minus lambda. Okay. Now this determinant we need to find it, which is equal to 0. Now AD minus BC formula, AD minus BC, 0 into 5 is 0, equal to 0. Now this. Now multiply this, lambda square minus 4 lambda plus 3, right? Lambda into lambda square, 3 lambda, here 1 lambda is minus 4 lambda, 1 into 3 is plus 3 equal to 0 is a characteristics equation. Okay. Now roots of this equation. Now roots simply lambda values, right? 1 minus lambda equals 0, nothing but lambda equal 1. 3 minus lambda equals 0, lambda equal 3. Therefore lambda equal 1 comma 3 are eigenvalues. Okay. Now this is a way to find out the characteristics equation and the eigenvalues. Now next go to proceed the problems on Cayley-Hamilton theorem. Now to see the problems on that, first see the theorem statement, Cayley-Hamilton theorem. Every square matrix satisfies its characteristics equation. A square matrix, just we see it, we discuss the problem that A, the corresponding characteristics equation we look at, that lambda square minus 4 lambda plus 3 equals 0. Now that characteristics equation satisfied by given matrix. Okay. Now that is a theorem statement, Cayley-Hamilton theorem. Okay. Now look at the problem to verify the Cayley-Hamilton theorem. Okay. Now first problem. Verify Cayley-Hamilton theorem for the matrix A. 3 1 1 minus 1 5 minus 1 1 minus 1 3. And hence to find the A inverse. The usage of Cayley-Hamilton theorem, without finding the determinant, without finding the using of the operation, simply you can find the A inverse or power of A, like A power 4, A power 5, A power 8 also you can find it by using Cayley-Hamilton theorem. Okay. First in this problem we have the two steps. First we need to verify the Cayley-Hamilton theorem. Next step we need to find the inverse of the matrix. First go for the first step to find the characteristics equation and its satisfaction. Okay. Now first A minus lambda I equal to 0. Now this determinant find it to find out the to get the characteristics equation. Now I have the shortcut to find the characteristics polynomial for 3 cross 3 very easily. Then otherwise we simply use the determinant. Now this into AD minus BC minus 1 into AD minus BC or plus 1 into AD minus BC. Now use that to get the characteristics equation. Otherwise, go for my method, go for logic, a simple trick. You're going to use it to get a polynomial. Okay, now the trick is a 3 cross 3 matrix, the polynomial of degree 3, okay, lambda cube minus, here sum of the diagonal entries of given matrix. Then sum of the diagonals are 3 plus 5 plus 3, right? Now that we need to write it into lambda square plus sum of the cofactors of the diagonal entries. Now this cofactor is 5, this into this. Now again diagonal cofactor, this cofactor, this cofactor, this cofactor. Now next step I clearly explained how can get the cofactors. Okay, plus sum of the cofactors of the diagonal entries into lambda minus determinant of A. Now this matrix determinant of A equal to 0. Okay, lambda cube plus lambda cube minus sum of the diagonals into lambda square plus sum of the cofactors of the diagonal entries into lambda minus determinant of A equal to 0. Plus minus alternative changes equal to 0. Now apply that. Now lambda cube. Now sum of the diagonals like 3 plus 5 plus 3. Here 3 plus 5 plus 3 into lambda square plus next diagonals cofactors. Here first diagonal of cofactor. Now this cofactor, this row and column deleted, remaining entries AD minus BC. That's why I wrote 5 minus 1 minus 1 3. 5 minus 1 minus 1 3 plus. Now next here second diagonal entry cofactor. Now this row and column deleted, remaining 3 1 1 3. Now I write it here 3 1 1 3. Okay. Now next third diagonal entry cofactor. Now this row and column deleted, 3 1 minus 1 5. Here 3 1 minus 1 5. That into lambda minus determinant of the matrix. Now determinant is 3 into any row any column cofactors sum, right, corresponding their entries. Now 3 into the row column cancel, 3 into 5 minus 1 minus 1 3. Now minus 1 into row column delete, remaining minus 1 1 3 minus 1 1 3 plus 1 into this row column deleted, minus 1 5 1 minus 3 minus 1 5 1 minus 3 equal to 0. Now this you simplified to get the characteristic equation. Lambda cube minus 3 plus 5 8, 8 plus 3 is 11, lambda square plus here 15 5 3 is a 15 minus 1 into minus 1 is plus 1. Okay, plus 1 plus, so minus AD minus BC, right, plus 3 3 is a 9 minus 1 plus 15 minus into minus 1 is here minus 1 into minus 1 is plus 1. Okay, into lambda. Now this calculation do it equal to 0. Simplify this to get the characteristic polynomial, that lambda cube minus 11 lambda square plus 38 lambda minus 40 equal to 0. Now this is a characteristic polynomial. Then our Cayley-Hamilton theorem should be satisfied this. That's why by Cayley-Hamilton theorem every square matrix should be satisfied its characteristic equation. Okay. Now this we need to satisfied by the matrix. Matrix is A. Side equation nothing but the A should be satisfied this equation. Simply replace lambda by A. If it is equal to 0, then it's satisfied. If we won't get the equal to 0, it's not satisfied. Now go for substituting in place of lambda. Now here simply take it for in place of lambda, take it for A cube minus 11A square plus 38A minus 40 we have. Then all our matrices you should be have a matrix. Into 1 we have nothing but in identity of matrix, identity element in a matrix is I, that is I. Then if you substitute these all values here, you should get 0 here. Okay, now this will give a 0 matrix. Okay, first A cube. Now A cube I shall directly write it here, but we can use a calc to find for A cube, matrix cube and matrix square here, and matrix and identity matrix of same order. Okay, now this I explain in a later, then how we can to go for finding A square, A cube by using a calc. Okay, first look at the problem. Is A square a cube, a square, a and I. Okay, now simplified here. 25 minus 11 into 9 plus 38 into 3 is 113 minus 40 is the first position entries. Now second position 39 minus 11 into 7 is minus 77 plus 38 here 0. Okay, like that we need to simplify each element position. Then when you simplified for each term, 0 0 0 0 0 0 all entries are 0. Then the polynomial, when you substitute in place of lambda as a can get equal to 0. Then we verified Cayley-Hamilton theorem. Now we need to find, next step we need to find for inverse of that. Now by Cayley-Hamilton theorem we should be equal to 0. To find the inverse of that, simply multiply both sides of a equation with a inverse. Okay. Now a inverse into a cube minus 11 a inverse into a square plus 38 into a inverse into a minus 40 a inverse into I equals 0. Now a inverse put aside, now remaining into the other side. Now this I put it this side, now remaining you can get it here 40 a inverse equal to a square minus 11a plus 38i. Okay. Now next a inverse equal to 1 by 40 a square minus 11a plus 38i. Now just before we find for a square and a cube, but we require here a square only. A square write it, a write it and I. Now simplify this to get for a inverse. See here the beauty we have for this Cayley-Hamilton theorem, without finding the determinant of the matrix we are finding a inverse. Okay. Now this is a way to find for the inverse of the matrix. Similarly you can find the power of a matrix also. When I want to get for a power 4, simply multiply this polynomial by a. Right here a power 4. Now remaining write it here, you can get a cube term, a square term, a come. Then that terms you apply for a power 4. Get for a power 5, simply multiply with the a square. A power 6 we simply multiply with the a cube to get for the powers, conjugate to powers of the a. Okay. Now this is a way to get for the powers and the inverse of the any square matrix. Okay. Thank you.